So, dear colleagues, good morning, everybody. Now we start the next thing of our workshop, and the first presentation session will be done by Professor Corrado Laggio of the University of San Diego, Italy, invited to the state of the malware and the event games. So, Professor Laggio, please start the presentation.
Good morning. Am I audible? Well, sorry for being late, but I had some problems with my connection. So I go to present my talk. Can you see my presentation?
Yes, you can see your presentation.
Thank you very much. Well, my talk will face the state of the art of malware. Malware is a buzzword coming from the merging of malicious software, and it stands for every kind of software program which is written to harm networks or a software system. And in my talk, I will give you some elements for understanding which are the current risks connected to malware and which are our possibilities and opportunities to face this problem. Well, the today agenda will comprehend a very brief history of malware, the state of the art of the malware technology, and some very relevant points in terms of attacks and defense. So, which is the possibility offered by machine learning for classifying malware. I will talk about a new brand risk for generating very aggressive malware, which is the generative adversarial network technology. I will talk about the main evasion techniques used by malware in order to evade the recognition and the classification, and then I will draw some conclusions. So just a very brief bio sketch about me. And I'm an associate professor of cybersecurity at the Department of Engineering at University of Sannio. I'm also the head of research and development of Defense Tech, which is a company in Rome which develops technology for defense and for aerospace. And my main topics of research are, of course, malware analysis and malware classification and software security. Well, what we are looking at now is one of the first malware appeared in the wild, which is called Cascade. As you can see, this is a DOS, a DOS environment, and this malware does a very amazing thing, even if disturbing. So at a certain point, what you see on your desktop, sorry, I go forward, is this. So you see letters dropping in the desktop. Of course, this is a disturbing behavior. But as you can see, this is not that harmful. After a while, in 2000, the love letter virus appeared. Actually, frankly speaking, this was one of the first worm. It was very easy because you received a mail like the one you are looking at in this slide, and the mail is supposed to be a love letter to you, and there was attached a file which was a Visual Basic script. This worm just corrupted some files in your machine, but this very easy and how to say pretty ridiculous worm created millions of damages around the world. Nowadays, we experienced the ransomware. The ransomware is, let's say, the very killer application of malware. So in the history of malware, ransomware is the first malware with a very successful business model. So the idea is that I encrypted your files, somehow I take your files away from your computer, and then I give you back your file only if you pay me a ransom. The evolution of ransomware is the so-called double extortion. So when the attacker obtained your file, in order to convince you to pay as soon as possible, a part of your file are published in some forums in the darknet. So basically, they sell a part of the file they stole you. Well, this is a very brief history of malware, of course, because there is no time for a complete history of malware. But the point here is that the evolution of malware was really very fast. And the people who develop malware are really focused on the development of a very successful business model, because of course the first purpose of developing malware is to make money. So the first point I want to highlight to you is the very fast evolution of malware. And in order to understand how fast is this evolution, I want to tell you the history of Pythia and not Pythia. Pythia was delivered in the 2016, and it introduced in the malware technology a very new technique, which is the microkernel. So the idea is that when Pythia arrived on your machine, Pythia overwrites the main boot record with a microkernel. So the idea is that when your machine is infected, your operating system is completely down. Your machine is completely entrapped in the microkernel, which is the operating system of Pythia. And then Pythia realizes also a complete wiping of the memory. So you have no opportunity at all to recover your files. After a couple of months, just a couple of months, NotPythia evolved in NotPythia. This malware was called NotPythia because it was really very, very similar to Pythia, but with some very important differences which make PITIA much more aggressive and evasive than PITIA. So the first evolution was the use of eternal blue exploit. Eternal blue exploit was a governative toolkit which was leaked by some governative agencies, and this toolkit was used in order to exploit, to leverage some vulnerabilities which were not known to the community. And this was the first point. The second point was that NotPetya is a worm. This is a very important difference, because when you write a worm, when you have a worm, this means that the malware is executed without the interaction with the user. So the user is not requested to execute any file, any program, to open any document. When the worm arrives on your machine, the worm executes and propagates completely in an autonomous mode. The third new element was a legal reboot of the machine. This was a very smart solution, because when you have a legal reboot of your machine, so a programmed reboot of your machine, the user usually has no suspect at all about the fact that you have a malware on the machine. It's usual to have a programmed reboot on your machine. So, till now, the point is, okay, we have people who write malware in order to make money, usually to make money. Of course, make money is not the only goal of these people. Of course, we have also other kinds of purposes, like terrorism, for instance, like cyber war, of course. But money usually is the main purpose. The second point is that the people who develop these kind of things have developed really software houses. So in these software houses, people work very hard in order to understand how to improve their malware. And this work is a 24 hours work. It's not hobby, it's not leisure, it's a very hard job for hundreds of people in the world. So we have to give numbers of the current scenario of malware distribution, because numbers help us to understand well the dimension of the problem, of course. The dimension of the problems is that in the 2022, we had more than 1,000 million malware in the wild. 1 billion malware free to go around in our machine. 1 billion. It's really a huge number. Among this malware, 80 millions of malware was never seen before. So we are talking about an industry. Malware is an industry. And as an industry, malware has a lot of investments. Malware has a lot of infrastructures. Malware has very organized groups which are really similar to companies for operating. Then we are looking at another kind of evolution, which is targeted malware. So the idea is that I don't write any more malware for which fits for all. I just target a very huge organization. I study the organization, and then I write malware that is able to infect successfully just that organization. Of course, the return on investment in this case is very high. We are talking about 5, 10, or more millions US dollars in this case. Another very huge problem is the zero-day marketplace. So the zero-day marketplace started 20 years ago when researchers and let's say hackers studied the vulnerabilities and the weaknesses of systems. At the starting of this history, there was not a very marketplace of 0 days. It was very difficult to sell a 0 day. After a while, a lot of people understood the importance to have a 0 day, so an unknown vulnerability. And this started a marketplace of 0 day. You have to understand that a 0 day may be sold at 10,000, 100,000, millions of US dollars. We have companies whose core business is to search for 0 days. This is a problem, of course, because with such growing volumes of money in this marketplace, we have also a lot of workforce involved in this kind of activity. So, which are the problems when we have malware? Of course, when we have malware, the first problem is to understand that we are looking at a malware, because a malware is a program, just a program, as millions of other programs. So the first problem is to understand that the program that you are looking at is a malware. And these problems is known as malware recognition. The second problem is the malware classification. So after you have understood that that program is a malware, you have to understand which kind of malware you are looking at. Because of course, malware never comes out from the scratch. Malware has a genealogy. Malware is the results of evolution from other malwares. So we can say that it's very rare to see a very brand new malware. Usually what you look at when you have a malware is the merging of previous malware, the evolution of previous malware. So the problem is to classify the family of malware. Of course, the problem is very hard because you have not an oracle. So of course, we don't have collection of malware in order to say, okay, I'm looking at a malware belonging to this family, because malware is a product which is not for the surface marketplace. It's a kind of product that must be hidden. And so the problem is also the clustering. So put together malware which has common characteristics in order to understand that that malware belongs to the same family. In this case, machine learning is very used to do this kind of tasks. The problem is which features, for instance, we have to use for recognizing successfully malware. And as you can see, till now, we can use a lot of feature, really a lot of feature. So we use machine learning in order to classify malware, and everyone uses machine learning for classifying malware. But this solution is successfully in some cases, but this solution is very weak for a plethora of reasons that I will tell you in a while. The first problem is the course of dimensionality. We have too many features to observe. And of course, machine learning produces models which must be explained, because machine learning is not semantics. So machine learning produces models which must be explained for the analyst. And sometimes models produced by machine learning as not a motivation at all, cannot be explained at all. We have a lot of studies actually for investigating if machine learning is effective for classifying malware, but I shall say that these studies are not reliable at all. The literature in this area is very rich of papers and very rich of investigations, but the results do not converge at all. In this slide, you can see a structure of the kind of features that we use in literature in order to study malware recognition with machine learning. As you can see, we have really a lot of feature. We have features which can be extracted from the structure of the malware. We have features referring to the behavior of the malware. And each one of these features can be obfuscated by the malware. And the other problem is that we don't have an oracle. This is really a problem. And this is one of the main hurdles for this kind of research. So if I should summarize the main problems of machine learning for malware classification and recognition, I shall say that the main problem are the two biases, which is the spatial bias and the temporal bias. Basically, the spatial bias refers to the unrealistic assumption about the ratio of goodware to malware in the data. We know the goodware because the goodware are in the surface of the marketplace. We don't know all the malware, of course, because the malware is underneath the surface. So we have that we don't know the exact number of malware. We don't know all the malware, and so we don't know all the structures and the characteristics of malware. The second bias is the temporal bias, which refers to the temporally inconsistent evaluation that we do when we build knowledge base of malware. So the malware that I use for training a classification today could be not valid to represent the malware of tomorrow. And this means that I have to train again my classifiers. The point is that, for instance, I don't know when my classifier get obsolete. I don't know the frequency of obsolescence of my classifiers. Then we have main issues regarding the research in machine learning applied to malware. The first is the quick obsolescence of the dataset. So we use a lot of dataset which are obsolete, and it's very hard to build this dataset because you have to think about that we have to capture malware, to analyze malware, and to label malware. And this requires a lot of time. So today we use datasets of 1 or a couple of years ago. And we know that this kind of research is not completely reliable. We have incomplete coverage of datasets. So we have, for instance, a lot of malware for Windows, but not for Linux or Mac. We have a lot of malware for Android, but not for iOS. We have a lot of malware for workstations, but not for SCADA systems. The other problem is to which extent we can trust the dataset. So when we think about the dataset that we use for our research, I have to trust the researcher that created that dataset. The last point is that the dataset polarizes the research. Of course, I can do research, the kind of research that the knowledge contained in the dataset lets me. Okay, now we have a very great problem which is the generative adversarial network. And I can bid that the new generations of malware will be created with GAN. So the idea of adversarial samples is that we use artificial intelligence in order to build malware which is not recognized by classifiers. So to build malware which has the characteristics of goodware. The generative adversarial network, the GAN, was firstly used in the field of image recognition. As you can see in these two pictures, you can see the first picture at the left, your left, which is a genuine picture. And this picture is perfectly recognized by a classifier. The second picture is the same picture, but it was altered by a GAN. The GAN basically altered the distribution of pixels in the image. But as you can see, the image remains basically the same. So a bare human eye is not able to recognize the difference. But the second image is recognized by a classifier as a bear, an animal. So you can see how powerful is the GAN. Of course, for machine and deep learning, we have a lot of other problems. The first problem when you use machine learning or deep learning is the high time required to learn when the size of features is very high. And the number of samples is huge. The problem is that if you want a good classification, you need a lot of features and you need a lot of samples. So if you reduce, the number of features or the number of samples, the accuracy of your classifier gets down. The other problem is that the training data set usually is not representative of the actual population of malware. Deep neural networks, so deep, the so-called deep learning, helps us in these kind of problems because it requires less, a smaller data set, and it requires less time in order to have a higher accuracies. But the problem of representation persists. So machine learning and deep learning has some limitations, and we have to know it in order to understand that this tool is very limited in this area. But now we have to understand how generative adversarial networks work for malware. The idea of generative adversarial networks is that you have a competition about two neural networks. The first neural networks is a generator, and the second neural networks is a discriminator. So the generator produces profiles of features for the malware, which are supposed to cheat the classifier. The discriminator is a classifier which receives the features produced by the generator and classify them. So this competition between the generator and the discriminator consists in obtaining a loss of accuracy of the discriminator. So the generator produces the first set of features, the discriminator recognizes a part of a set of features, and then the generator obtains a feedback from this classification. And this cycle goes on till the accuracy of discriminator goes down under a certain threshold. Under a certain threshold of accuracy loss, I mean, the generator can be told that is successful. So these are very complex architecture of neural networks. In our laboratory at this moment, we are working a lot on these architectures. We have developed a prototype for generating malware with GAN, malware for Android system and for Windows system. And now we are working at a prototype for generating adversarial network attacks with GAN. And what we can say is that these architectures are really effective for now. So the problem now is to investigate how to recognize these adversarial samples. The other very important point when we talk about malware is the evasion technique. What is the evasion technique? The evasion technique is a method used by malware for avoiding the recognition. Basically, we have four kinds of evasion technique. We have obfuscation. Obfuscation is a technique that is used for hiding the code of the malware. And obfuscation includes different techniques. such as polymorphism, code packing, code encryption, and code protection. Of course, when you have an obfuscated malware, usually it's very hard to reverse engineering the malware and to extract features from that malware. Then we have Packer. Packer are engines for compressing executable, and usually Packers are used for avoiding the reverse engineering of malware and for injected malicious code into the processes of malware. Then you have Cryptor. Cryptor is a very widespread technique. Cryptor means that your malware is encrypted. Usually, malware is encrypted in order to avoid the hash recognition of malware and in order to, of course, avoid analysis of malware. Protector is an obfuscation technique which consists of a chain of encryption and decryption. And this chain, these different cycles of encryption and decryption makes very hard to obtain the code of malware. According to let's say a recent report, the 1% of the malware using advanced evasion techniques are detected by controllers. So what I'm telling you now is that we are looking at malware that use very effective evasion technique. So we now have problems to recognize malware. So another point of my talk is just that one. The evasion techniques are getting harder and harder. And this is a problem because we are talking about 1% of malware using advanced evasion technique, which is recognized. I shall say one thing about the recognition of malware, because the point of the recognition is not whether you are able to recognize the malware, but when you are able to recognize the malware. So the point is that you have to recognize the malware when you are infected, on when you are attempted to be infected. Because if I recognize a malware 1 month after I get infected, of course, this is useless. The point is that I must recognize the malware timely. That's really the point. So when you say, I'm not able to recognize the malware, I'm really saying I'm not able to recognize the malware timely. Of course, we have also network evasion, which is a kind of evasion aiming at cheating all the controller of network traffic, like, for instance, firewall or IDS. In this case, a lot of techniques are used, like packet fragmentation, which is usually a fragmentation technique that allows the attacker to hide the traffic. The session splicing, which is a continuous splicing of the same session the same connection, and actually very small payloads are sent into the network. A lot of attacks just target the memory of intrusion detection system, and they try to produce overhead of these memories. Then we have covert channel communication, consisting of using unused header of the packet or to conveying information by modulating the system behavior properly. And then we have traffic obfuscation, which is just an encryption of the traffic between two endpoints. As you can see here in this slide, of course, I don't want to read you all the lines of this table, but what you see, the meaning of this sliding, or the meaning of this slide, sorry, is to show you how many pickers exist today. But the point is that the known pickers are not used by the strongest malware. For the strongest malware, every group of malware production realize its own picker. In this case, it's much more difficult to detect the picker used, and if I cannot detect the picker used, I cannot unpack the malware. And if I cannot unpack the malware, I cannot analyze the malware. In this slide, you can see the main techniques used by the pickers. So we have the compression, which is the original technology of picker. We have the polymorphism, which is a technique, for which uses the encryption and which changes frequently the encryptor of the malware. Then we have the code overwriting. So we have techniques for changes the code of the malware. And then we have code virtualization. Code virtualization means that the malware uses virtual machines in order to execute instruction. This kind of malware is getting widespread now, and this is a very evasive malware, because you can imagine that you see malware which call virtual machine, and the instruction of malware are executed in tailored virtual machine. Of course, we have also a classification of picker complexity. As you can see, we have 7 levels of complexity of picking. And what this means is that the sophistication of malware is growing very quickly. So one of the point that I'd like to leave today is this very high velocity of growing, of improving, of enhancement of the malware. So the technologies used for writing and protecting the malware are getting harder and harder, more and more sophisticated. Each month. It's not a matter of years. It is a matter of months. Well, of course, nowadays, the 80% of malware is picked, And this means that a malware analyst loses a lot of time in order to understand how to unpack the malware. And sometimes this means that the analyst has to execute the malware in virtual machines, and this requires a lot of additional time. Basically, a packer is a compression routine which put the code in the data sector of the portable executable, the file, I mean, the executable file. Usually, the packer has a stub, and this stub extract the malware, the code of the malware, decrypts the code of the malware, and executes the code of the malware. When the malware is baked, for the analyst, there are a lot of problems due to the fact that the analyst doesn't know where the malware is, where the entry point of the real malware is. Because usually the entry point of a malware is located at a fixed place. So basically what the result is this malware is not recognized by the automatic tools of malware classification. Usually these malware just reconstructs selected calls because packet malware is smaller than usual malware. The only weakness point of a packet malware is that also this malware needs to be executed. So there is a moment when the code of the malware is placed in memory. I'm going to draw the conclusions of my presentation. Well, the conclusions, my conclusions are made of two parts. The first part is that nowadays we have to consider an industry of malware. And this is a very serious point. So we have a lot of people working very hard, 24 hours a day, 24 hours a day, 7 days a week, in order to produce the best malware they can. They have a lot of money, they have a great infrastructures, they have the best skills in this area. So the first item of my conclusion is this. Now we have to look at the malware marketplace as an industry, a very rich industry, a very powerful industry. The second item is the malware evolves quickly. The malware is studied in order to harm our systems. Every line of codes of the malware is studied for that. Every line of codes. So the only way we have to fight against this phenomenon is to put in place the same force, a similar investment, a similar infrastructure, and similar skills. Okay, this is the landscape for me. And what you see here are the directions of research in malware analysis. So the first point is the incremental learning. We have to know how to continuously improve our classifier. The second point is the active learning. So we must continuously select the better samples we can that represent the malware landscape. The prediction of malware prevalence, we have to stay a step behind the malware. We have to predict which are the new trends of malware. Another huge point is the adversarial learning. We will see in the next years a lot of adversarial attacks, but we don't know how to recognize that. And this is really a trouble. Malware attribution. An important point is to understand who realized the malware, because to understand the authorship of malware sometimes tell us a lot of information about what the malware will do. Malware triage. We have to improve our ability, our capability to analyze automatically the malware. Malware detection in its infancy. The most infamous malware campaign used malware which was submitted months before in the public sandboxes. So a lot of campaign uses malware which is known months before the campaign, but no one was aware of that. This is a problem. Of course, we have to improve our machine learning capability, and we have to reduce the cost of machine learning. Thank you for your attention. Sorry again for being late, and if you have any question, I'm here. Thank you very much.
Thank you very much for the presentation. Now, this question. This is how the problem is because like to cover but it's a little bit too much. The first Professor representing the with the malware detection. I have some questions. The first one, you mentioned about the 0 day. One of the malware started to destroy the computers. Okay. So looking at some statistics from the past, how many 0 days have taken place and what was the damage for computer industry and not only?
I'm sorry, but I don't hear. I cannot hear very well. The audio is a little bit noisy. Is it possible to repeat the question, please?
Yes, we will try to repeat the question. Closer to the microphone.
So, hello another time. And
Yeah.
Professor, I would like to ask you about the 0 day when malware is activated and destroys the computers. Okay.
Yeah.
So, could you tell something about the history? How many times in the past this was take place, and what it was a damage for computer industry and not only?
Yeah, sure. Thank you for the question. Well, we have observed this kind of malware, especially for the industrial systems, because the idea of this malware is to abuse the control system of SCADA, usually, so industrial control system, in order to activate it, processes, physical processes, which can really destroy machinery. There is, for instance, the destroyer malware, which is in the wild now, and which is a malware targeting industrial system. We have also to remember Stuxnet. Stuxnet was a malware which was able to destroy nuclear reactor. Usually, what they do on a computer is the wiping of the memory, or they can create hypes of voltage in the computer. How to say, the term that the hackers used is to freeze the computer when you use this kind of malware. But especially for industrial system, we are looking at an increasing, a growing interest in this kind of malware, destructive malware for industrial system. So yes, thank you for the question. It's really a very huge problem.
Thank you very much. And another question, you taught in your report that around of 80% of the malware are detected by different software, okay? So, but another 20% also are was very dangerous, okay, and destroyed the systems, okay? So, could you estimate in the dollars, euros, the damage of this 20%?
Well, I have the exact amount of damages, but perhaps I could say that the forecast for the 2025 of the malware marketplace is about 10,000 billions of US dollars. Of course, the damage is very difficult to estimate. But if you consider that we are talking about a marketplace, a volume of affairs of thousands of billions, you can imagine the volume of damages, which is somehow proportional to this amount.
Okay, thank you. And my final question, possible you can recommend some companies which are most successful on the market and can prevent the malware. Could you tell something about this one?
Oh, yeah. Yes. We have, actually, in the last Gartner report, we have the companies, like we can see Falcon, we can see SentinelOne, CrowdStrike, which are very successful company. I should say that now we have this EDR and EPP technology, which is replacing the traditional antivirus for two reasons. Because now the antivirus is embedded in the operating system, and now we have the EDR technology, which is a technology that is aimed at recognizing the kill chain of the compromise. So what I can suggest is to move toward this kind of technology. This is the first point. So the first point is to have this kind of technology. What I suggest is to improve your ability to do threat intelligence. Threat intelligence now is really, really, really important because it's the secret for reducing the window of opportunity for the attackers. The second point is that we have now a lot of different technologies for protection. And what I suggest, especially to medium and large companies, is to have all these technologies in action. So this is my main suggestion for replying to your question.
Thank you very much.
Thank you. Thank you for inviting me. Thank you.
More questions? No questions. Thank you very much.
Thank you.
Now we have a coffee break till 11 a.m. and then we have next two presentations.
Okay. Now it's time to start the next presentation. I am glad to ask Professor Luca De Vito, Department of Engineering, University of Chisinau in Italy, to speak about spectrum monitoring and localization of radio frequency emitters. Luca, hello, how are you?
Fine, fine. Thank you. Thank you. Nice to see you.
Nice to see you too. So could you please start the presentation?
Yes, yes. Please tell me if you're able to see my presentation.
Yes,
My
we
screen.
can see you. We hear you very well.
Can you see? Can you see it in presentation mode?
Yes, yes, it is the presentation mode.
Okay, so thank you, Professor Paladi, for the kind introduction. So it's Luca De Vito from, I'm Associate Professor at the University of Chisinau, Italy. I work with Professor Da Ponte and same institution of Aaron Visaggio, who talked just some minutes ago. My talk will be about the spectrum monitoring and localization of radio frequency emitters. Okay, let me introduce first of all the outline, my presentation. So I will first a little bit talk about how radio spectrum monitoring can help security protection, and so what is the involvement of radio spectrum monitor within security. And then I will talk about what are the requirements and challenges for devices and systems for radio spectrum monitoring. And then I will tell you the experience of our group in this field, in particular applying compressed sensing for radio spectrum monitoring and localization in the framework of a project that we have funded by the Italian Ministry of Defense together with a company the same company that Aaron is actually CEO. So it's this Defense Tech, which is based in Rome. And this project is called Z-Spectrum. And so I will tell you the experience, the activity that we conducted in the field, in the framework of this project, and in particular, the design of the radio spectrum monitoring acquisition node and how we are carrying out localization of hidden RF emitters. And then I will tell you what are the current open issues and some conclusions. So radio spectrum monitoring is quite an important task in several applications in the field of security. It allows to observe the radio spectrum emissions, and it can be helpful for such kind of application, like, for example, critical site surveillance, for example, the surveillance of embassies, airports, where the access and communications are restricted. And we can, thanks to the identification of communication, we can identify threats and, how to say, some kind of non-cooperative with people. And also in the field of maritime security, in Italy, we have a lot of problems with some people coming from Africa, and so radio spectrum monitor can be helpful to patrol the maritime channels to search for some people, for search either for some people who is in who need rescue, for example, but also to identify possible crime activities. And also for border security in general, when there is a border, we need to protect the border and to identify possible threats in borders. And radio spectrum monitoring has been also used for drone countermeasures, for example, for identifying some drones. Drones are often remote controlled, and this remote control is actually visible in the spectrum, so that we can, thanks to radio spectrum monitoring, we can even identify and localize some drones. And in general, also, it is used for what is called the signal intelligence. That means not only to detect some signals in the air, but also trying to receive and understand what is the content of such signals. So I present here some applications, some application examples in the field of radio spectrum monitoring, and in particular coming from the literature. And in particular, in this case, this paper proposed some spectrum monitoring to identify and localize people needing rescue. So in this case, they proposed a UAV with a spectrum node on board that patrols the sea and can receive messages on several frequencies to coming from people that needs help in the sea. So this is one application, but we have another in this slide. In this case, it is for critical site surveillance. In particular, what is shown here is an airport. And in this case, we have a scenario where there are some hidden radio frequency transmitters. And this paper proposes a swarm of UAVs also equipped with some kind of spectrum monitoring to identify and localize such hidden transmitters. So, but let's understand what are the requirements for radio spectrum monitoring systems and what are the challenges. First of all, a radio spectrum monitoring system should be wideband and or, but in many cases this and stands multi-band. That means that they must observe a wide band and often even several bands simultaneously, because sometimes the radio frequency transmitters are hidden and we don't know what is the frequency this kind of emitter actually transmit. So we need to observe a wide band and several bands simultaneously. And this is even more important with next generation communication systems, which are very, very wideband. Another requirement is that such kind of systems should have a high dynamic range. That means they should be able simultaneously to detect signals which are with very difference in the power levels, because they can be at different distances from the monitoring node, and that's the reason we need a very high dynamic range. Then another requirement is that often we need synchronization of multiple nodes, such to acquire the same signal simultaneously on several nodes, and this is helpful either to, in the case one signal is not detectable in a particular node, but maybe it is in other nodes, and also to provide some service of localization, some kind of localization of the RF emitter. We will see later in our project how we face this and what are the problems in synchronization of data acquisition nodes. Another requirement is that it is needed accurate node positioning. So the nodes should be equipped with high accurate positioning, because to localize a hidden radio frequency node, we have to know what are the position of the acquisition nodes. And another requirement is that we need a wideband transmission, so a high data rate transmission from the acquisition node towards the command and control center, because sometimes, as in the case of signal intelligence, we don't need only to detect the signals within the acquisition nodes, but we also need to understand what is the content of the communication, and this is often done by sending all the data that are acquired by the acquisition node remotely towards a command and control center where there is this kind of intelligence. So for example, decryption and also the merging together all the information coming from the different nodes. And the main challenge in the design of the radio spectrum monitoring, this comes also for the experience we have with the Italian Army, is that often the acquisition system, they have the capability of acquiring a very wide band, but what is the bottleneck is the limited bandwidth, the limited data rate from the acquisition node towards the command and control center. So what happens often is that nodes are able to acquire a wide band, but they are not able to stream such huge data rate that is acquired towards the command and control center, and therefore they should decrease the bandwidth to observe a smaller bandwidth, such to have the possibility to send out all this information. So our group is trying to solve, trying to face this problem, this challenge of limited bandwidth from the acquisition node towards the command and control center. And what we proposed is the use of compressed sensing for radio spectrum monitoring. So in this slide, you see the comparison of two systems. One is based on traditional signal acquisition that is based on the Nyquist sampling theorem. And below, you will find the same path using this new technique, which is called compressed sensing. I will talk a little bit later about the theory of this technology. So the idea is that we have some signals that can be, for example, at different frequencies, like that showed in the spectrum on the left. And usually a radio spectrum monitoring is based on what is called a vector signal analyzer architecture with some kind of mixing by a local oscillator and the reception of the signal by an intermediate frequency, which this is an example with the signal being around, for example, 10 gigahertz and with an intermediate frequency at around 1.5 gigahertz. And we can see that in the upper scheme, the sampling frequency should be about several gigasample per second. For example, in this case, it's 6 gigasample per second, and producing a data stream which is quite huge data rate. It means it is 5 mega records per second, and if one record is about 1,000 samples, it means giving out a data rate which is in the order of 6 gigasample per second. And instead, below, we can have the same application and with the same signal with a similar analog architecture, but we could exploit this new technology of what is called analog to information converters, which actually implements the concept of compressed sensing. And it is possible to decrease the sampling frequency to, for example, in this case, it is about 500 megasample per second. And this allows to decrease by a factor of about 10 the data rate which is needed to stream out from the acquisition node. What is needed, however, is how to say, processing block, which is spectrum reconstruction on the other side. Okay, and we can see that in this case, we have a huge reduction of the data rate. And another thing that it is quite useful in the field of security is that the signal which is acquired and is actually sent from the acquisition node towards the command and control centers, it resembles like it is like a noise. So it is somehow coded by a sequence which is known only in the acquisition node, and that brings some kind of intrinsic security to the system, which instead how to say instead in the case of the traditional acquisition, we have that the signal is actually understandable, and so anyone that is able to receive this kind of messages is able to see the acquisition and also to understand what is the information that is carried by, which is carried by. And so in that case, in the case of the traditional acquisition, we need some kind of additional security layer, so some kind of encryption, which could be not needed in the case of compressed sensing. So this is the comparison between the advantages and the disadvantages of this new technology, compressed sensing, compared with the traditional Nyquist sampling. So the advantages of compressed sensing are, as I told you, a lower data rate. We can even have a lower sampling frequency if we use a hardware realization of compressed sensing, because we can either implement compressed sensing in hardware or in software. In the case we have implementation in software, we use the Nyquist the sampling rate, and we only reduce the data rate that is used in transmission. In the case of hardware realization, we even reduce the sampling frequency. And as I told you, the signal is noise-like, so it is intrinsically secure. So we don't need any additional encryption, because the signal is actually encrypted by using as a key a pseudo-random sequence that we can even change in time. So it is intrinsically secure. The disadvantages of compressed sensing is that there are some requirements. So the signal must be sparse in some domain. That it means that there should be some domain, like, for example, the Fourier transform domain, where the signal should have only few non-zero components, and this is a requirement. We will see a little bit later. And we have also a risk of losing information if the signal model is inappropriate. So, for example, if the signal is not as sparse as we thought. So we need to model somehow the signal, and within this signal model, the signal should be sparse. The coefficients should be sparse. And another disadvantage is that we cannot, as transmitted signal is noise-like, we cannot directly we cannot directly display the signal, but we need some kind of reconstruction, which is a more computationally intensive task compared with simple display. But this is actually done only when it's needed. So we can think about an infrastructure where we acquire the signal and we tag the signal with a timestamp, for example, and we store such kind of signals in a compressed form, such that we can even save storage resources, and we only reconstruct the part of signal that we want to display or to understand. On the counterpart, in the case of Nyquist sampling, the advantages is that there is no risk of losing information because we actually acquire all the information that we sent, all the information without any compression. There is no requirement for a signal model because we only have the samples of the signals. But the disadvantages is that we have a high data rate, a high sample frequency that we cannot reduce, and the signal which is transmitted is an understandable signal, so an additional layer of security is needed. Some information about this theory around underlying compressed sensing. So, as I told you, compressed sensing assumes that the signal is sparse in some transform domain. So we can think about that this domain is the Fourier domain, which is widely used in the field of telecommunications because telecommunication signals, they are well separated in frequency, and often the radio spectrum is not fully occupied, but only a small portion is occupied by signal in a specific time, while instead the other part is actually empty. So in this case, the signal xn can be thought as the how to say representation, its representation in the Fourier domain by means of those coefficients theta in this formula. And the requirement is that the vector of the coefficients theta 0, theta n minus 1 should have only a few number of non-zero elements. So this norm is as this zero subscript. That means that it is called the L0 norm. That means counting the non-zero elements of the vector. So the number of the non-zero elements of this vector should be less than a value which is s, which should be much lower than the record length, which is n in this case. And so if we can assume this, but okay, it seems like a strict assumption, but this is not, because most of natural signals, they are actually sparse. And as I told you, most of telecommunication, most of the spectrum that I'm going to acquire is only occupied in a very small portion of this radio spectrum. That means only few thetas are actually non-zero. So under this assumption, we can obtain a compressed version of the signal xn using only a linear transformation, which can be represented like this formula, which is just a summation, or we can think about like a matrix multiplication by a matrix phi and a vector of the elements x, where this phi mn, so is the number m of the output samples is lower than the number of the input samples, and that means that we have some kind of compression. And this ratio between n and m is actually what is called the compression ratio. So it means how much we are able to compress. In some cases, this compression is just a selection of the samples, which can be done very, very fast, because we don't need to process some, to evaluate some kind of processing, but we only do some kind of selection of the samples according to a specific law. For example, we can think about some kind of pseudo-random sequence, which is 0 or 1, and we can only select those samples of the input signals according to the ones of the pseudo-random sequence. And that's what is called non-uniform sampling. So we are trying to apply this kind of concept in a project that, as I told you, was funded by the Italian Ministry of Defense. This is called the Z-Spectrum project. And the objective of this project is to build up a network of wideband spectrum acquisition nodes and a command and control center. So the idea is that the nodes acquire the signal in a wideband and compress those signals using compressed sensing, and send the compressed samples to the command and control center. So we can think about some vehicles, for example, equipped with, but they can be even unmanned aerial vehicles, for example, that are equipped with an acquisition node. We have a radio source which is unknown. We don't know neither the position, we don't know the frequency, and we don't know the position of this node. And the idea is that we are able to detect this kind of signal, to compress the radio spectrum that we acquired. We send the spectrum to the command and control centers, where the waveform reconstruction is carried out, and the emitter is actually localized. So at the end, we are able to receive the signal that is transmitted from the radio source, from this hidden radio source, and localize the location where this source is transmitting. And to do this, we designed an spectrum acquisition node based on a quite new device which has been issued by Xilinx. It is called the Xilinx ThinQ UltraScale Plus radio frequency system on chip, RF SOC, which is a very special device that merges together analog devices like, or not analog, mixed signal devices. So it means analog to digital converters and digital to analog converters. We can see in this scheme on the right lower edge, this is the scheme of this chip. So in this chip, there are analog to digital converters with quite huge sampling frequency. For example, up to, in this case, in the case of the device we are using, it's up to 4 gigasample per second, and also some digital to analog converters with update rate up to 6 gigasample per second. Then there is some programmable logic, so some FPGA core where that you can program, and for example, in this case, we can add the real-time processing of the acquired samples. And there is also a processing system with some ARM Cortex A53 cores, 2 cores, ARM Cortex A53 with running a Linux operating system. So we can just use the mixed signal part to acquire the signals, use the programmable logic to make some kind of real-time processing, and may carry out the remaining processing and the network managing using the processing system in the Linux operating system. And using that chip and a board which is called CCU111 that is provided by Xilinx, we designed a spectrum acquisition node that is actually done by this scheme. So we have a omnidirectional antenna with a low noise amplifier. Then we have a mixer that receives the local oscillator signal by a voltage controlled oscillator, which is actually controlled by digitally directly from the main board using a Arduino board, which is actually used only to translate the interface from USB to SPI. Then downward of the mixer, we have a low-pass filter, and we acquire the signal. So this ADC number 1 is used to acquire the signal coming from the main antenna, this omnidirectional antenna. And then we have another part which comes from a GPS antenna, which is actually used for synchronization of the nodes. So all the nodes are taught to acquire simultaneously according to a GPS clock. So we have a GPS antenna here and a GPS receiver. This receiver has a time pulse output, which can be programmed to give out a pulse at a certain period. For example, in this case, we used 100 milliseconds period, and this pulse is given to another channel of the Xilinx board, such that we can use this signal as a trigger for the acquisition of the other channel, ADC1. So this is actually the architecture. And then inside the Xilinx board, we have also a software running on the Linux processor that takes out the samples from the memory of the FPGA. So as I told you, there is an FPGA that makes real-time processing, and then this processing is put on block RAM. Then it is read from the Linux system, and it's sent through Ethernet towards the command and control center. So I give you some further details about the implementation. As I told you, this is on the top scheme. For example, there is on the left the radio frequency data converter, so the ADC that is on the device. And the processing is actually divided in 2 parts. This left part is within the programmable logic of the FPGA, and the right part is within the processor system. So we have the synchronization, so the trigger function and filtering within the programmable logic, and instead compression and transmission is within the processor system. And on the figures below, we have a highlight of the programmable logic. So programmable logic is done with the main scheme on the left. So we have the reading of the data coming from the radio frequency ATC, and for the signal part, there is a part of digital down conversion, filters, and decimation. And instead, for the trigger part, there is just this block of trigger detection. And everything goes to the block RAM, which is actually triggered by the output of the trigger detection block, such that the RAM actually stores the data only when there is a positive edge of the trigger which has been detected. And we can see on the right part below the chain which is used for digital down conversion, filter, and decimation. So the acquired signal is actually modulated by a numerical controlled oscillator to produce the digital down conversion. The output is around 2 gigasample per second. And then we have a chain of filters that acts by low pass filtering the signal and decimate by 2. And there is finally a selector which allows to select properly the bandwidth that we want to store. So there is actually like a knob in the software that allows to select the bandwidth, and according to this bandwidth, the user can take the output of these filters. And this is given to the block RAM for storing. From the software part, it's a little bit more complex because we have a system which is based on a server that you use to configure the application, and an application which is the blue one in this case, which is used to take data from the FPGA part and give to the network towards the command and control center. So I go a little bit faster because I'm lack of time. So I show you some experimental results for the signal acquisition. So you can see that we are able to acquire the signal. This is actually without compression and with the sine wave as acquiring signal. And you can see that we have what is the result in the time domain upper part and in the frequency domain lower part with the different bandwidths. So bandwidths can be 800 megahertz, 400 megahertz, 200 megahertz, and 100 megahertz. And we can see here the results. And on the right, it is shown the spurious free dynamic range within the order of 70 is higher than 75 dB, which is quite good. This is instead we using a QPSK signal, so you can see that we are able to see the signal with quite a high accuracy, and again it is shown in the upper part in the time domain. You see actually two waveform in the time domain, which is because this is the output of the digital down conversion, and so the signal is complex. So you see the real part in blue and the imaginary part in orange. Instead, on the lower part, it is shown the frequency domain. And this is using compression. So in this case, we use the compression ratio equal to 8. And you can see that this is showing the results with the sine wave. We can see that we are still able to get the signal in the spectrum. And in the time domain, I don't show you because it's a noise-like, so it's we cannot understand it. And we can also measure again the spurious free dynamic range that we see that in this case decreases with the increase of the compression ratio. So it is, but it's still quite good, at least up to some values around even 20 compression. So we see that we are able to compress sine wave with up to 20 factor up to 20. And instead, this is the using the compression and again with the QPSK signal instead of a sine wave, again with the different bandwidths, and we see that we are still able to detect the signal. There is just a little noise, which is actually due to the image of the down conversion, because you know, when you down convert, we actually multiply by a sine wave and then low pass filter, and this is actually the residual after the low pass filtering that we find in the spectrum. But we know the position, so we can just discard this. And this is a short video of this is a short video of the our acquisition node is packed in this system. So I show you, I'm sending now a signal with this generator on the bottom, and simultaneously we monitor the signal using this spectrum analyzer. All the signals are by radio, so using antennas. The video, I'm sorry, is done in our lab, so quality is not very good, but it's just to show. And this is the acquisition. So you can see that even we are quite fast in the acquisition. So there is one acquisition every 100 milliseconds. This is with a sine wave. Yeah, you can see that we can change the frequency, and the system is able to follow the signal. Then we change to a QPSK signal. And we see again the signal. There is some noise, which is actually due to the environment of the laboratory, which was not very clean. And let's see with the compression. So in this case, we see the compression. So we have a software on the computer that receives the data from the acquisition node and is able to produce the spectrum of the signal again. So signal is compressed in the node. Compressed samples are sent to the computer, which reconstructs the waveform and gives you again the spectrum. This is that was with sine wave, and this is with the QPSK. And this is the results with the QPSK. You can see that this is a little bit larger band. Okay. So, but as I told you, we are not only interested to receive the signals, but also to localize the emitters. In localization, we have mainly three options. One is basing on the receiver signal strength. Another is based on what is called time of arrival, and another in this case it is based on what is called the time difference of arrival. So the most popular is actually the receiver signal strength. That means I'm measuring the power, the received power on the different nodes, and according to the loss of power that I have, I try to trilaterate to have to understand where is the source. So the advantage in this case is that we don't need synchronization of the receivers, and that, or at least I don't need very precise synchronization. I need in any case synchronization, but not precise synchronization. But and disadvantages is that it can be affected by what is called the log normal shadowing. So it means that the atmosphere actually modulates a little bit the amplitude of the signal due to humidity, change in the uniformity of the atmosphere, and that can bring error in the measurements. And usually we cannot have a very high position accuracy unless we use a very huge number of nodes. Other options are based on time of arrival, but this requires a very high synchronization in the receivers and even knowing the information of the transmission, so that is only applied, can be only applied when I know the transmitter. I control the transmitter, and that's not the case that we can imagine. And the latter part is about time difference of arrival, that in this case there is actually no sensitivity to log normal shadowing, but and no sensitivity to what is called the synchronization error. That means that we can have slightly, we can have a bias in the synchronization among the node, provided that this is fixed bias. But we need a very precise synchronization of the radio frequency receiver, and it is a very highly sensitive. This method is very highly sensitive to the uncertainty of the synchronization. So I'm going a little bit faster because I not have so much time. But so we tried, first of all, localization by RSS. We made some simulations, but I want to just showing our latest experimental results that we are currently doing. So in this case, we have some experiments with 4 acquisition nodes that we realized and 3 transmitters, and a transmitted signal which is an OO keying at 5 megasimple per second. And we have just applied the 2 techniques of time difference of arrival and receiver signal strength. And we can see that in this slide, we show the distribution of the times of the time difference of arrivals that are used to localize. And we just have one problem, is that over 120 frames, we have that not overlap between the time difference of arrivals of 2 different acquisitions. That means that there is a bias in the clocks, which is not constant in the during time, and that's don't allow us to have a very precise localization. So it means that we are able to localize with an error which is in the order of 10 meters, which is not very good. And we just investigate a little bit better, and we found that this is due to the drift of the GNSS clock we are using, which deviates. You can see on the right part, we did these trials with 2 different GNSS boards, and we found that there is this drift, and this drift is quite huge, so in the order of 100 nanoseconds, which doesn't allow us to get very precise measurement. So this is a preliminary results that we had, and so we need to move to a more precise GNSS synchronization board. Instead, for receiver signal strength, we can see that we have overlap in the distributions. In this case, it's distribution of the power. It's not distribution in the time, because the power is used to localize, and we are able to localize with a certain accuracy. We can see that this asterisk is the position, the original position of the transmitter, and the circles, the blue one and the orange one, are the actual estimated position. So we are quite close, in the order of 1 meter, which is better than before. So with RSS, we are able, with TDOA, we need a more precise clock. And similar is with compression, that doesn't give us such. So the problem is actually synchronization, is not compression. So in conclusion, I showed an application of compressor sensing for radio spectrum monitoring, the localization of hidden radio emitters. I showed the prototype of the acquisition node that was realized based on this new architecture, which is called SynQ radio frequency system on chip. And the experimental results show a good reconstruction of the received waveform, even with compression ratio of 8. Localization has been experimented using RSS and TDOA. TDOA, we saw that it is very depending on the accuracy of the synchronization, in particular on the drift of GNSS clock. So we need to find a very, very precise GNSS clock. So we are thinking now to use some kind of temperature compensated clock, or even better clocks. instead for the RSS, it allows localization with an acceptable error, so in the order of 1 meter, but we expect some performance decrease as the distance increases, so we need to conduct further test with longer distances, which was in this case in the order of 10 meters between the nodes. Yeah, we can see here it's about 20 meters is the square. So here are our references to our papers. So if you are interested more in this, I put here the first 2 references of the applications and then our papers. So if you are interested, you can read more and also contact me for any other information. So thank you so much. I was quite in time, but I started a little bit later. But so I'm ready to answer to your question. Thank you.
So I think that there are many questions, but we will try to limit ourselves to a few one because we are behind the schedule. So first question is from Mr. Please. Maybe you will come here. The microphone is here. The microphone is here, and please come. This is your
Hello.
Dear Professor, thank you very much for your presentation. And in your report, you show the 2 very hard problems. The first one is the signal detection.
Yeah.
And another was signal localization.
Yeah.
Of the area. Yeah. So could you tell me what is the probability of correct signal detection? The first one.
Yeah,
Usually,
yeah.
and approaches.
Yeah, we actually didn't evaluate yet this feature because actually it depends on the signal to noise ratio. We are more interested in this phase to try to get a system working with a certain value of the noise power, but it depends highly on the distance of the transmitter towards the receiver. So our idea is that we can provide a network of acquisition nodes. We could improve this kind of detection because detection is actually, how to say, critical when the signal is quite low within the noise. But we think that if we use a distributed system of several sensors, we can improve this by jointly, how to say, by using the information coming from all the distributed system. So this is the idea.
The question. You mentioned about the accuracy of signal localization.
Yeah.
From 10 to 20 meters. So is referring to the static emitter or dynamic one?
No, it's static until now. We only, yes, we only tried with static transmitters. We are also interested in some, how to say, some moving transmitters in the next stages of the research. But in this case, we only tried with static transmitters. So yeah, but in the case of dynamic transmitters, we can even apply some systems of tracking like Kalman filters and so on to start from initial guess and then try to improve this guess basing on even the distribution of the movements that can be possible.
Are you using the response processes?
I'm sorry, I didn't understand.
Are you using fast Fourier transform processes?
No, in our case, we are not using. Yeah, we are using fast Fourier transform only in the reconstruction side, so not in the FPGA, because as I showed you in the FPGA, we are only using digital time conversion, which is realized in the FPGA, and field filtering and decimation. So the real-time processing is quite simple. It's not so difficult. Instead, fast Fourier transform is instead used at the receiver side when we need to reconstruct the samples, because in that case we either if we use no compression, we don't use compression, we just take the Fourier transform of the samples. If we use compression, we use a fast Fourier transform within the reconstruction algorithm to take the samples.
Thank you very much.
Yeah, you're welcome.
Just
Hello,
short
Bartosz.
question.
Yeah.
You, adapt your results to or to get more knowledge about that, because we have a similar project now. We are just it's the responsibility of a partner or not ours, then just to detect the signals in broadband frequencies, but we are using it from the one location, not from the nodes. So maybe we can just get some idea from your research.
I'm sorry, Bartosz, I didn't hear very well. So can you go closer to the microphone?
Yeah, of course. We are doing the similar project, but we are detecting signals from one location, not from distributed ones. We just get few antennas on rectangles, so that to get the direction of the signal that is received. So I was asking if it's possible to have some information of your project, some results of your project available, or it is all classified, so you can share it.
No, actually, they are not classified because they are public. So we are publishing papers, so they are not classified because we don't have restrictions until now from the Italian army. We only need their permission to publish, but we usually do before starting a publication. So all we publish is public. Is actually public, so it's not classified. Even because they didn't give us classified information about the frequency to be used and so on. So we are just trying according to our thoughts without their inputs. So that is interesting what you are doing. You're actually using angle of arrivals, which is another approach to localization, but we preferred to use instead RSS or TDOA because it allows us to use a very simple antenna, which is just an omnidirectional antenna without need to have, for example, rotating systems. Because usually for angle of arrivals, you have a very directional antenna, so you can only detect in a specific, how to say, range of angles, and otherwise you need to have some rotating system, which has so if you have a vehicle, for example, you can equip the vehicle with a motor that allows you to rotate the antenna. But we don't want this because we wanted to have a system which could be, for example, equipped like a backpack of Hermes, and so which could be maybe lighter.
Yeah, thank you. So I will just look online for the publications. Yeah, thank you.
We keep in touch. Thank you.
Thank you.
Any more questions, please?
Oh, we thank you very much, Luca.
You're welcome. Thank you. Thank you for the opportunity.
So next presentation is entitled Hardware Solution for Cybersecurity. And I would like to ask Professor Galia Farinova from Faculty of Telecommunication, Department of Technology and Management of Communication Systems of Technical University of Sofia in Bulgaria. Professor Farinova, do you hear us?
Hello, do you hear me? Yes.
Yes.
Okay. Hello to everybody. Thank you, Professor Palati, for introducing me. Thank you, Professor Da Ponte, for inviting me in this project and to this workshop. It has a very interesting development. We started organizing it some time ago. It was postponed several times. And when finally it took place, it overlapped with another event that I was organizing, the international conference IFSIP. And this is the only reason for me not to come live, because I like Chisinau, I like Moldova, and it was in my plans to be on site. So please, I apologize for that. But I arranged the program of our conference in a way that I close it just before my presentation. So now I am happy to share with you some of our ideas. Next time we'll have better opportunity to meet online. I would like also to congratulate the hosts to organize such an event in, of course, this complicated time. But even more, one reason more to talk about security. So, I am from the Department Technologies and Management of Communication Systems in the Faculty of Telecommunications at Technical University of Sofia, Bulgaria. My name is Galia Marinova, and I would like to present some of our recent studies on hardware solutions for cybersecurity. What is the contents? Of course, some words about Technical University of Sofia, about our work in the Laboratory of Computer-Aided Design, using tools like Cadence, Vivado, etc., and fast prototyping, systems on chip, FPGA, software-defined radio, PCB, etc. Then to mention some elements of hardware aspects of cybersecurity, some of our projects like crypto modems, encryption IP blocks, intellectual property blocks, random bit and number generators, proof, logical encryption, security for IoT, cryptocurrencies, cyber physical systems, autonomous cars, etc. So my university, Technical University of Sofia, Bulgaria, is 75 years old university, ranked #1 in engineering in Bulgaria in the national rank list, which is updated regularly. We have 14 faculties in my university. One of them is the Faculty of Telecommunications. In our faculty, we have about 200 students in the first year studying bachelor degree. Then also we support the master and the doctoral program. My department is Technologies and Management of Communication Systems. We are working on computer-aided design and fast prototyping. Currently, I have 7 doctoral students in my group. So what about hardware security? Why emphasizing on hardware, not only on software? This is, as we can guess, much faster at high speed. We can implement our security algorithms compared to what is done through software. So this is the main reason to implement security into hardware. And the other aspect is how to securize the topology or the program or the circuit itself from different attacks or piracy attempts to steal the design of a circuit in certain cases, etc. So it is a large area, and there are even conferences on hardware security specialized every year. There is a classification of algorithms in this area, depends on what level we are working, because we are going really at the lowest level, even at the level of the gates, of the level of the layout, and also an RTL level or at the system level. So we can find different hardware obfuscation algorithms like IP encryption, RTL locking, white box obfuscation. At gate level, we have logic encryption, FSM blocking, protocol-based debug scan structure. Layout, we can make camouflaging, monolith split fabrication, and split fabrication, 2D and 3D. Also for PCBs, we can implement obfuscation in order to make the PCB more difficult to the threats from cyber attacks, and also in emerging techniques like circuited nano device enabled, which is now a big area. There is really big issues, and I would say, because I'm also teaching nano communications and nano networks, so this is really a big issue. There is very few done in this area, and it will be a very big area in the future because it concerns our health or other elements or the environment. So we have to be very careful here. Okay. So I will give, I don't know if I put the correct presentation. Yes, no, excuse me, I have to upload, excuse me. I will stop just for a minute because I'm afraid that I uploaded not my final version. Yes, excuse me, because I was not recognizing exactly. I uploaded from somewhere else. Okay. Yes, the effect of managing two events at the same time can lead to this sometimes, but I hope that I will get out of the situation quite fast. Okay, here I'm on the right place. Again, many apologizes for this. Okay, so I mentioned in the beginning several areas where cybersecurity is critical, and especially emerging technologies, not only nanotechnologies, but all that concerns IoT, cryptocurrencies, cyber physical systems, autonomous cars. It is really object of a very big concern about cybersecurity, because through a cyber attack many of these systems can be transformed into weapons. It is not very difficult to imagine how it can be done. So it is not here just to take private data or something else. We can really create weapons and harm people. In these areas, we all know standardization is just starting, and all which concerns clouds, artificial intelligence, nanotechnologies is a very big concern about cyber security. So in my group, we are mainly concerned on hardware aspects of cybersecurity, as I said. So we have worked for years on different projects. Even some years ago, we worked on developing a crypto modem. So to integrate in the description, in the topology of the modem, the encryption blocks. Or another option, it was to develop intellectual property encryption blocks, as for example, the advanced encryption standard cores. So it was created in our group. We created one of the first realization of encrypted modems. Then we had a very big research on pseudo-random bit and number generators, which as you have noticed, are really in the basic of any system of security. As an engineer in electronics and in microelectronics, of course, and somebody who has worked on discrepancy of elements and statistical analysis of integrated circuits, the POOF method is also a part of our study. Also, logical encryption that I mentioned some slides ago. Also, there are additional elements that we have studied together with the encryption devices. This is what it adds, because actually for encrypting something, we are adding something to the circuit. So it takes more place, it consumes more power. So these aspects are, and the fact of consuming more or emitting more, it is helping. It is giving the opportunity to the adversary, to the hacker, to recognize our key, actually. So we are very careful when making the additional elements for security, what we are adding as power, as emission, electromagnetic emission. Also in this aspect, I will give an example of some realization that we made recently together with our colleagues from REN, Central Superec N, using SDR software-defined radio devices, how we can actually catch the ICE keys just by using an analog PCB very close to the digital PCB, and we can recognize the key, actually, so break the ICE algorithm. So the first research global that we made on random bits and numbers generators for cybersecurity, because this type of devices are used for authentication, password and key generation, digital signatures, cryptographic protocols, and other challenging messages, etc. And usually the quality of the random bit or number generator is defining the level of security that we have. And also we are working on the circuits of random bit and number generators, because we are still staying on hardware in our research. So how can we say what is the quality of a generator? Of course, we can never be 100% sure on what is that it is really a random set of bits, but there are sets of criteria standardized as the 15 NIST criteria, or the small crash and big crash from Montreal, which can give us a certain level of certainty that our bits or numbers are really random. Because the quality of the generator, the fact at how many criteria it is passing for randomness, it gives the level. This is the main feature which defines the level of the main criteria which defines the level of the security. If we put just we don't have a random number of bit generator, it is the lowest level. If we have one, we are one level more. And if this generator is proved through NIST or crash or other tests, so we have the highest level of security. If you have just had a look on some classifications of the level of security, you will certainly notice that. So some years ago, we made a very big study of different random bits and number generators. We compared as the reference of the Marcenet Twitter generator in MATLAB, and all of our realizations were described on VHDL, implemented on FPGA, and studied with the NIST test. So we have found finally that the golden generator is one of the best solutions compared to Kazami, compared to the basic generators that we have, Fibonacci, LFSR. About the physical unclonable function, this is something that I feel very, very close to me, because I have worked a lot on statistical analysis on the fact that any circuit has actually some discrepancies from the geometry, from the topology and geometry that we have. So this leads, of course, in a small discrepancy in the parameters of the circuit at any level. And usually it is a drawback for us, because the functionality also of the circuit is shifted. But here, surprisingly, for cybersecurity, it has a very big positive characteristic, because these discrepancies, because they can never be repeated, they're really unique for each circuit. So from there we can extract the so-called digital fingerprint of the concrete circuit, integrated circuit, and it can never be, how to say, repeated from somebody else. Actually, it is impossible. So this is a very good identification of a concrete system on a chip or any other integrated circuit that we are using, one of the best methods. So using something which was for us a problem in the past, how to avoid all these discrepancies or to decrease them. Actually, now we are using this for creating the digital fingerprints of each one produced chip. This is just the modem that we have realized some years ago. It was also in the framework of NATO projects. And I would say we presented in London on a congress, and it was really the first realized, because we started from the very beginning describing all the blocks of the multi-carrier modem in VHDL, then realizing on FPGAs, and including the advanced encryption block algorithm. So it was one of in the transmitter and also in the receiver. So it was really something very successful, and even we were awarded the best award there on this congress. So we mentioned the different methods that we have. So recently, some of my doctoral students, we decided to make this small experimental setup for studying logical encryption. So we have a circuit, and we have an encrypted circuit on a hardware. So the encryption itself, it is hardware realized. So we compare and we see what kind of encryption, how the different encryptions affect the behavior of the circuit. Again, it is VHDL, it is based on FPGA realization implementation. So I will just show the principle with something very simple, just to remind how it works. So if we have an original circuit, we can add an element somewhere to combine a signal, and there is a combination of bits which form the key, which combination or which value doesn't affect the behavior of the circuit. So depends what is my encryption based on, but for a certain value, the behavior of the circuit will not be affected. So if I form a key with several bits and several gates or several additional elements put here in there and the circuit, and I know what bit to input in order not to change the behavior, I can create a key with as many bits as I want. So I can put it on different places, of course, and the affection will be different in case if I have the wrong bits for the keys. And there are big studies to see how it can be done, so that with the minimum of additional elements, we have a higher security. So adding elements, of course we increase the area on the system on chip or on the programmable circuit, and also we increase the power consumption. So in any study that we are making, even for the random bit generators, even for the encryptions, we always follow also the power consumption that we add. So it is just shown how is the initial circuit working, and how if we make some wrong bits, how we can generate here and there bits which are wrong. It is not necessary that everything is wrong, but from time to time it can give something wrong if we are not with the good keys. So this is just a very simple example to show how many combinations, how many possibilities this simple principle can bring to us. So we made some study with the inserting different elements like multiplexers, like flip-flops. We saw what are the estimations in literature. For example, the XOR itself brings a very low level of security, and additionally, the XOR circuits are those that consume the most power. So this is really good for illustration, but it is not good for realization. There are others with flip-flops and multiplexers which are giving medium or higher security. The flip-flops gives the fire. Okay, since these encryptions, there are different attacks that can quite easily break them. So here there are some elements of the study with additional blocks, like, for example, the different elements. So here the keys are with more bits. And the results, you see, we can have a few wrong bits. We can have many wrong bits, depends where we put our encryption. The power consumption is followed and quite, how to say, increased in some cases, especially if we use the basic elements. So the others, if we can include the multiplexers here and there on different places, but here the examples are with 3 bits. Also, we have seen the inserted wrong bits and wrong results, and the power consumption, and also the area on the chip. And the last was with flip-flops, just in order to first to see which of these 3 elements, and to confirm that of course the flip-flops are the best for security, and for power consumption the multiplexers, which are worst in both. It is always the XOR and XOR gates. They are just for illustration. So from there, we can, of course, search in a more complicated circuit the best positions for these additional elements, and the length, how many, how much, and where to put them in order to achieve the highest security, and to add as less as possible area or power consumption. So this is with flip-flops that we study. Also the power consumption. our work now is to develop a block for a data center, for securizing a data center, because data centers, clouds, and these areas are very vulnerable and very much attacked. So we are working on such a block, and we hope to soon be able to show the good results with the hardware security on it. It is just an example to see here how these additional effects, which are not in the functionality, like power consumption, like emission, can actually make us access the key. This is an example that we have made together with our colleagues in Central Supelec using mixed digital and analog PCB. And in the digital PCB, we have the encryption. And then we have here emission with antenna. And on another board, with the based on software-defined radio, we were collecting data, and we obtained the image of the electromagnetic field, the values. So from these values, we could surprisingly deduce exactly the key of advanced encryption, and it was 128-bit key, which was completely broken in our experience. It is why it is not enough to see the functionality by itself, by behavioral simulation or other, because these secondary effects, emission, power consumption area, they can open your key through other matters. So these are several papers that we have written in this area, and if somebody around is working also on hardware security, we would be very interested to communicate and to discuss more on further projects. Thank you very much for inviting me. And again, apologize if I made some small mismatch.
Thank you very much, Professor Marinova. Questions, please? So I have only one question. If your system hardware permit to realize time data process or exists delay, not?
Would you please repeat, because something I didn't hear very well.
Oh, yes.
Please, would you repeat the question? I could not very much.
Tell me, please, if your hardware permit to realize real-time data processes or exists some delay?
Yes. The short answer is yes. It permits. Yes.
Thank you very much.
Thank you.
Other questions? No. Thank you very much, Professor Marinova, and all the best to you.
So in the conclusion program, we have here ready for lunch. Thank you.
Thank you very much. Bye-bye from Sofia.
You can show me.
Just in case we.
Oh, but close the door.
I'm not sure.
I'm
Răspunsul mai comod sta. Bine.
in ways that people are told leads to.
But let's start. I salute you. Good day. My name is Anton Danic. I'm the founder of our company. Basically, what is our main goal is delivering aircraft that is user-friendly in the field. Given I have some field experience using UAVs worldwide, the main problem and challenge for the operator in the field is the assembly, disassembly, and the operation itself of the aircraft. So, what is the problem from the perspective of the operator? So, first thing you have to do when you arrive to the spot, on site, you have to take the aircraft out of the vehicle, you arrive to the site, you have to assemble it, you have to prepare for the flight, and then you have to execute the mission. What are the challenges? So, there are a lot. First, most of the aircraft out there need tooling to be assembled, need cables and connectors to be powered on, need a lot of subsystems to be verified on site to make sure that they're working properly, that they're connected, so on and so forth. So how we have managed to solve this issue is making the aircraft modular. By modular, I mean when you arrive to the field, you just have to assemble a big Lego constructor, that's it. You don't have to have cablings, connectors, tools, or any other thing. So basically, what you have to do to assemble aircraft is just to snap on until you hear a loud click, and that's it. For instance, to assemble, you have to take it off, and you take the wing, and you are gone. And when you arrive to the field, you need like 2 minutes in a crew of 2 people to assemble an aircraft. In one person, it takes like 4 minutes. So what you have to do to assemble any module of the aircraft is just to slide it in, and you know that all your connection is done, mechanical and electrical. And then there is a secure lock for each to stay put in flight. So that's our approach on solving the issue of field operation for preparation in the field. Can do other than that, other than being user-friendly, is that having, let's say, 2 types of aircraft built on the same ecosystem, by combining the modules, you have like 6 different types of aircraft. You can go from runway configuration to VTOL configuration in a matter of minutes. All you have to do is to swap 2 of the modules. Let's take the runway. You can see that this module here goes to the rear, to the tail, and it's short just for the runway configuration. So what we have to do to transform this type of aircraft to VTOL is just to take this module off, take this one, install instead, and you have a VTOL with the wheels, with a gasoline engine. This one is with the electric propulsion for the cruise. The same applies for the engines, so for the propulsion systems. We have an entire propulsion module here. So the propulsion module, which is here, you can see the fuselage is split in two. So if we take out the canopy, you can see, you can watch closely. You can see that the fuselage is split. It's held by 6 nuts, 6 bolts. So that's what you have to do to swap, let's say, the payload bay. Those payload bays are interchangeable. Have different types of payloads with you, and during the mission, tactically swap those and get different outcomes, basically with the same equipment. This is for payload base. Same applies to engine base. At this moment, the 3.5 meter wingspan, which I like the most because of its agility. The cruise speed is like 160 kilometers per hour, and the maximum speed like 200 kilometers per hour in this kind of wingspan. So it's very agile. You can solve let's say swift operations. While with a 6 meter wingspan, the flight is more floaty. So you get more like a soaring type of flying, like a glider, with a cruise speed of 20 meters per second. So that's like 72 kilometers per hour. So basically, what you can do in the field is also swap the wingspan of the aircraft by adding some inserts, which are like 1 meter inserts here. You can add just these inserts, and you are done with a larger wingspan aircraft. Another thing is the flight time. Due to the limitations of today's lithium polymer technology, for the electric version, pure electric version, we can achieve like 2 hours of flight time at most with that type of aircraft, while with a simple gasoline two-stroker, we can achieve about 3 hours of flight time with a 5-liter gasoline canister. Furthermore, there is a third option available today also that we deliver, is a 4-stroker engine with electrical fuel injection system, an onboard generator, an onboard starter. That's very fuel efficient, and in the same configuration, we can achieve like 8 hours of flight time while recharging the batteries on board. So even in VTOL configuration, we can take off the lithium polymer batteries, and while we perform the cruise, we recharge the batteries and have just enough power to perform the landing stage of the operation. Talking about control, we have a simple ground control station that we've developed using the same field experience of ours. What it offers to the operator is generic controls, stick controls for the aircraft in case you need to pilot it manually or semi-manually. You have a number of switches to turn on and off different modes. Another thing you have is Windows 10 personal computer that runs a mission management system on it with a 2K resolution touchscreen. Let us power it on while I speak. And a television to get the live feed from the aircraft. We don't use any high gain antennas attached to our ground control station, as that's another limiting factor while operating in the field. So you have always to be focused on placement of ground control station in order to get a good signal to the aircraft. What we do instead is we are running low power antennas and transmitting equipment in the ground control station and use a system of relays to relay the signal to the aircraft. This way the operator can be at any time in a secure place running the mission and the relay systems are relaying all the controls and delivering the information back to the operator on the ground. And another thing with our aircraft is transportability. So while we are watching this 6-meter aircraft that takes almost all the room in this hall, for transportation we would need a box not larger than 1 meter and 20 centimeters long, half a meter high and half a meter wide. Given the modularity of the aircraft. So none of the modules exceeds 1.2 meters in length it's along this side. So I'll take off this wheel here. So basically, this is the size of the largest module of the aircraft. And while assembled, the placement is optimized, we can achieve quite a small form factor for transportation. Just in case it interests you, everything you see is done in-house now in our company with the efforts of our team. Every project, all the materials, everything is done from raw materials, from raw structures. So nothing basically besides electronics is outsourced. So given this point, I will be more than glad to answer any questions that might arise within our company.
Could you please start the engine?
No. No. Even if I had the batteries with me, which I intentionally left at our company, I wouldn't do that because of security reasons.
Thank you.
Thank you.
What are the prices for both this one?
Well, it depends a lot on the configuration. There is not a fixed price because, for example, we can use a gimbal, a camera gimbal that's, let's say, 3-axis with dual sensor, with RGB camera, with a thermal camera, 30 times zooming, and that gimbal, let's say, markets for like 20,000 euro. And then we use basically the same gimbal, just running another LiDAR sensor in it for sensing the distance to the target. And that said, just this tiny option adds another 50,000 euros to the equation. So honestly, there is not a single answer to this pricing question.
Diapasons?
I would say pricing starts from 50,000 euros and up. 50,000 euros and up.
What kind of service do you use? What kind of service do you use?
Servos?
Are they metallic gear or just carbon gear as the usual one? How much torque do they show?
Yeah, well, the most basic servo that is installed in this aircraft is like 50 kilograms of torque. All of them are running titanium or steel gearing, so no plastics. And the commercial units of higher value are running split control surfaces with dual servos on each element. So 2 servos are controlled basically the same, but given the servos are bulletproof, that's just another safety measure that we integrate to stand by the aviation standards.
So can you make a conclusion that gasoline version is better than electric?
Not necessarily, because there are emissions that are, let's say, noise level sensitive. And internal combustion engines have a higher noise profile than electric ones. Also, the internal combustion engines have an exhaust. Maybe there are emissions that are exhaust sensitive. Let's say if we sense some particles in the atmosphere, we have to be as clean as possible in the ambience. So there is situation to situation approach. There is non-best solution existing.
So Europe was a Moldavian company.
Yes, we are 100% Moldavian company.
What is the name of this company?
Well, the name of the trademark, which is not registered at this point, is Danaero. Danaero, yes. And there is a number of companies that are involved in this project, but the trademark is Danaero.
The weight?
Maximum takeoff weight for this model is like 35 kilograms. For the large wingspan VTOL one is like 50 kilograms. But this is just the actual maximum takeoff weight. It's of course not the limit. Let's say for the 6-meter wingspan, the absolute limit for the airframe is like 150 kilograms.
What happens when if Windows 10 crashes?
Absolutely nothing, because there are, let's say, 3 modes of operation. One is full manual, other one is semi-manual, or let's say semi-assisted, and one is fully autonomous. So in case we're running a fully autonomous mission, we are not ground control dependent at all. We use it just for monitoring purposes. The aircraft executes all the phases of the mission, from takeoff to operation and coming back and landing, all by itself. So this is an autonomous scenario. It can be also an automatic scenario when the aircraft executes some of the elements of the mission in an autonomous manner, but it awaits some inputs from the operator, let's say some green flags for some sort of actions. And the third one is manual control. But given manual control, you have to be in visual line of sight. So there is not a plausible scenario that you will lose a radio link while having the aircraft in visual line of sight. Besides user error, of course.
I was waiting
I should refer to the IDOM project, the beginning of this activity at our university. We fill office and the laboratory courses, training trainers, and the professional internship, creation of the program itself, implementation of the program, and the deployment of the program till now. Thank you. I'm trying to say that the beginning of the education for drone in Republic of Moldova, and in particular the Moldova State University, began with this project, the very amazing, interesting project, educational for drone. This was Erasmus Plus project for 4 years, and everything. And every result of this project was possible with a great partnership with the University of Chisinau as the international coordinator, with Pascal Da Ponte, Professor Pascal Da Ponte as coordinator, and the other partners from EU parts, from France, Poland, and Romania, and Eastern Partnership countries, Moldova, Armenia, Georgia, and Belarus. I'm very proud, my colleagues, too, that another 24 associated partners joined our project during the project lifetime. I also would like to mention that Moldovan partnership was the most fruitful partnership within this project. We work together, 5 institutions: Moldova State University as coordinator, National Coordinator, Academy of Police of Moldova, Civil Aviation Authority, State Agrarian University of Moldova, and Academy of Public Administration. All together, we developed the program for continuing professional education and all activities within this project. The success of this project was predicted, maybe, or foreseen by the very ambitious objective of the project to provide higher education institutions in partner countries with efficient and effective instruments to set up offices for education for trans, for the transfer of knowledge regarding the mechanical characteristics of trans, detection equipment, processing and use of the acquired information, and the national and local laws regulating the used professionals of each country during the program of continuous education. And all the results in the export, all the synergy of the partnership and the objective managed to obtain such results. This is the main important results in our project. The 2 reports user needs in technology area, in drones technology area, and our report for the regulatory needs in the field of drones, 2 very important documents in our project. These 2 documents were the starting point for another activities in our project. The setting up of the 4 offices for education for drones in 4 partners in 4 countries involved in the project. Deployment, the courses for training teachers, the deployment of the program for continuing the professional education in area of drones, and the last but not the least, very important results were the e-learning platform for both for CTT and for the program for continuous education. One of the main objectives, as I said, was the offices, the creation of the offices and laboratory for education zones. This physical space, I can say, for the sustainability purposes, developed not only the educational process for university and for the program, but also research projects in the drone application areas, technological transfer activities, and other activities related to this topic. And the courses, all the results in these projects were oriented to the creation of 2 types of courses. The course of for training teachers. This course were developed once during the project lifetime in June, July 2018, exactly 4 years ago, at the Moldova State University. The course was assigned by the Minister of Education of Moldova with 50 transferable credits. And this course includes 3 modules. 1 big modules on drone technology, and 2 modules, 1 on drone laws and regulation, and another drone applications. This is some pictures from our very hot 2018 summer for all the partnership in digital project. We had 6 weeks course from 9 o'clock till 5 o'clock, 5 p.m. In each week, we had another teachers, another students, another lectures, practical activities, laboratories, and so on. After such an interesting 6 weeks, our teachers from Moldova, Armenia, Georgia, and Belarus were involved in 2 weeks professional internship in the EU universities. And after that, our way for developing the program itself. We create altogether the curricula, the papers, all documents for program for continuing professional education in area of drones. This was in 2018. Also, this course was recognized by the Ministry of Education and Science of the Republic of Moldova as a program for continuing professional education, and assigned 20 credits for this, and a very long and path for accreditation. This course from 2019 till the spring of 2020 in the pandemic period. This activity for accreditation was a big challenge for Moldova State University team because due to 2 factors. One of them was the change of the procedure of accreditation, the continuing programs in Moldova at the national level, and the second one, the normal pandemic period for everybody. But we finally managed, and the program was accredited for 5 years. And we can issue for each participant in our program certificate, but by the Ministry of Education and Science of the Republic of Moldova. The content of the program includes also 3 models: the technology of drones with 6 courses, drone architecture, drone avionics, drone equipment for measurement and monitoring activities, piloting techniques, processing of measurement data, and drone maintenance. The second one is about laws and regulatory items, laws for and some units of this model was about laws for privacy, risk analysis and prevention, limits in the usage of drones, rules for the documentation, flying permits, and flying certification and approval. And the last one, but not the least, very important part of our program, because this part is a flexible one, depending on the participant profile and requirements. And the deployment of our editions. We deployed since now 7 editions of this course, and all these editions were deployed by our amazing and fruitful fruitful collaboration with our partners from Moldova, as I mentioned, and the profile of attendance within these 7 editions were very different, from agriculture to mass media, technology, public security, logistics, customs security, public services, academia, cadastre, drone technology, and finally, just people interested in drone for personal needs. Also, our Moldovan partnership edited a handbook for this course, and a very important result, I think it's one of the most important results in our not easy times, in pandemic times. We developed e-learning content on the Moodle platform of the Moldova State University. Each participant have access. Each participant in our program have access to all of materials for this course. In this learning platform, we had a lot of videos, a lot of presentations, everything about drones in one space, virtual space. As you can see, we deployed courses in the pandemic period 2. Some of courses content we did in online version, and some of them in the laboratory according to a special schedule. Some pictures from our first edition, the start and end of the graduation of the first edition. Also, we had special editions just for border police of the Republic of Moldova, 7 weeks of courses, evening courses, according to the participants' needs and possibilities of our teachers. Also, we had a special edition for National Patrol Inspectorate. This was 3 weeks program from morning, from 9 in the morning and 7 p.m. each day, 5 days in the week, and also according to the participants' requirements. We had the edition, a special edition for Army, and also was a special edition, a special schedule for this edition also. With the schedule for different editions had different schedule, and each participant received each week another schedule for the next week. And everybody know where the course will be and so on. The final exam tests also elaborated by our partners altogether. And for being in the past time and to be more and more efficient, we applied a quality survey of each participant in the end of each edition of the course. I put in my presentation some aspects of this survey about our participants. Most of the participants of our program are persons between the ages of 30 to 50. Just a person between, people who correspond to the age capable of work and with possibilities of professional and career. And another thing, most of the respondents have work experience between 5 and 20 years. The interest for improving the skills and learn new aspects was the reason for choosing this program. Some aspects about the quality of our course, and these aspects like the accessibility of the course, the correspondence of the didactical materials and methods, and some other were appreciated by its contents as daily. And And about the models and the courses, all taught in the program for continuing professional education, it was evaluated as very important and need to be a part of the future editions. And also we asked participants for some suggestion for improving our courses. And there is some, I took some of them here. Selection of groups with the same background level and approximately equal areas. As you can say, we had some special editions after we received this suggestion. To introduce invisible application model, the topics about traffic monitoring and mass meetings monitoring. Our teachers try to introduce and to do some changes in this model. The practical activities and application focused on clinical projects, mapping, environmental quality, and so on, as my colleague Vyacheslav did it. Full practical hours and integration of some advanced parts in our models. And the last slide is about the impact of this program from different perspectives. From the perspective of professionals or people who attended our courses, they can acquire new skills and abilities to meet economic and technological challenges of the 21st century through the continuous program. And from the perspective of teachers, why not? They increase their professional competences and have opportunities to be involved in new activities in the using area. And diversification of the possibilities of continuous professional training for different professionals from different areas also was this program. In the end of my presentation, I hope our partnership, our partners from Moldova partnership work together within another next editions of this course and improve this program too. Thank you for your attention. If you have some questions.
Questions?
If somebody wants to be part of our program as students, you are very welcome. Thank you.
Thank you. This was our second project coordinated by Professor Dapoin. This project started in 2016 and the last had to be finished in 2019 for 3 years. But due to the pandemic, it was finished in 2021.
February.
And he actually, Moldova State University was lucky to have such a project because we could really establish a new laboratory in the field of drone, which is like a state-of-the-art laboratory, and nobody in Moldova has such nice infrastructure for education in the field of drone. So I will start my presentation, very brief presentation, because we have to finish today by 5:15, 3 p.m. And then we will have a coffee break and can discuss further issues. And tomorrow we will have the last day of our workshop, and I would like to kindly invite you to join us for the last day of our workshop, which will be held not in this building, but building Faculty of Physics and Semantics and Chemistry. And we will start tomorrow at 9 a.m. Professor Datau is here. First of all, Sergio will present us the infrastructure of the research center, then Karima, and after that we will go to the laboratory for education, where we could see more practical activities there. So I have just, I guess, about 10 minutes till 5 p.m. So I start briefly this presentation, which is focused on the advanced physical technologies with a UVS application in environmental security. This idea actually started in 2020 when we got approved research project by our National Agency for Research and Development. So we could continue our, let's say, not research, but our interests in the field of drones, in particular, using these techniques which has been developed at the Faculty of Physics and Engineering to do more research focused activities in this field. So let me start this slide. So now we have two projects ongoing. First is the research project entitled Advanced Physical Technologies for modeling environmental factors. This project will last till 2023, and another project which is only for 2022. It's an innovation technology transfer project of the EU for real-time start warning of the population of Chisinau in case of danger, special and anthropogenic hazards. So about this project, we will speak more in more details, and we ask our stakeholders to come tomorrow to our workshop. So my colleagues and in particular me, we will speak more about this, let's say, brand new project, because we think that in case of the city of Chisinau, when more than 800,000 people live, we should have such a nice system for online, or in real time monitoring and warning of the population in case of some hazards. Next slide presents a part of our research group. When we went to the laboratory outside the city, so Professor Ozovano is here with us. He's the head of this laboratory. We visit and use drones to monitor some, to test, let's say, some techniques in order to improve our both the system for taking samples to see the by using a special monitoring station, and having this data, raw data, to develop further software to acquire this data, and then to get some, not only, let's say, pictures, but also to try to predict some developments in the field of environmental hazards and so on. So we use the measuring station named SOVA, which is its functionality and the characteristics are shown here. I will not skip this slide. Also this one. And you will see tomorrow this station. These are pictures obtained during our experiments. And what can we see taking these measurements relates to air pollutants. So we have both gaseous and particulate pollutants, primary air pollutants, secondary and secondary organic air. So every measurement can be done precisely in order to monitor some pollutants related to every kind of these air pollutants. Some pictures were taken during our measurements. Okay, next one, we used so special software for photogrammetry, and the experimental terrain was presented here. In particular, we developed algorithms which can transform ground and aerial drone images in a digital map and 3D model. So we can rotate this model and see different sides of this terrain. So we can add this nice picture, interactive picture with real coordinates to our results, which are already transformed by our software, which has been developed in the laboratory. Some real experimental data here, some graphs which relates to 3D images of concentration of air pollution with solid microparticles PM10 and PM5. Why it is important to have this data, in particular when we will speak about tomorrow about this e-alert system to monitor the situation in the city, because it really affects the health of the population. And so just as a naive representation of this particles as on the size length of different particulate pollution. So it's within this range. It's larger than ultra-fine particles, but it's of course it's much smaller than, for example, fine beach sand. Okay, so if we consider the human hair here, it would be a grain of sand like this dimension, and one part of this of type PM25. It's just you see it's 5 such particles is contained in one part PM10, and 5 of these particles can be aligned along the diameter of the human hair. So it's about 20 such particles along the diameter of the human hair. So it's very small, and they penetrate deeply in the lungs of humans. So it's very dangerous to have high concentration. That's why we have a scale here and can measure so alert scale. Let's say when the level is too high, so it's already orange or red level when it is dangerous one. Also, we studied some, let's say, dynamics of air pollution before 2020, when we started this project, to see how are distributed the sources of the air pollution, in particular in the Republic of Moldova. So we found out that only 7% could be related to the emission from the stationary sources. So 93% are related to actually to the traffic. Why this is so high? Because actually Moldova is an agricultural country. That's why we can't say that we have so large industrial sites with high pollution. But cars, of course, are now the main pollution sources at the moment. That's why we now try to concentrate our investigation toward the emission related to the cars. That's why we developed, now it is under examination patent in order to capture the traffic related pollution and to study by using AFM, atomic force spectroscopy. This is an image obtained by a usual optical microscope. So when we take just, you see this is a square with 10 micrometer side lens. And actually this side, this spot, let's say, very, very small, was studied by using AFM. This is a new device which we succeeded to acquire in 2018. So it's really new. So the result is the results are very precisely obtained. So this is as I shown before. This is the whole surface of our mono crystalline silica. But when we take only this part of the surface, we can see by using AFM technology, so the picture like that. So we can see the topography of PM particles, but not only particulate matter, not only the dust, but these are actually, as we try tomorrow, Sergio will try to present us on the monitor this result or similar result to this. It's actually an aggregate of different let's say of particulate matter of different origin, not just sand, not just let's say it's aggregate of including organic pollutants and so on. So it's very difficult actually to do research by using atomic force spectroscopy. But my colleagues succeeded in getting these nice pictures. That's why we can now exactly say how large and how what is let's say the surface of this pollutants. And next step, of course, would be some analysis related to the structure, to the composition of these pollutants. But now we are happy because we can already see these particles and can say how does this particle look. Okay, and I try to be in time, so this question, and tomorrow we can continue by showing exactly these pictures and the station, how does we can get these results, and also the drone we have in the laboratory, and the software we have to process the experimental data, because we have actually a series of raw data. This raw data are sent on the server. Then we can get this data from the server. They always are kept there. And we try to use this data just not only to make some nice graphs, but also to make some maybe prediction about the future levels of this pollutants, taking into account where this data were obtained and so on. In particular, we are very interested to get this data in real-time regime. So, for example, okay, I will just give you an example. When we use the drone and we use this monitoring station and study at different altitudes the level of pollution, actually we get this data in stationary mode. So we have different points, but we consider the data are taking at the same time. But we are most interested in getting dynamical data in order to see how does this pollution change over the time. And in this case, we go from another point of view when we have the stationary points. In particular, in this new project, we will have 5 sites in the city, and these sites will get data, let's say, every 30 minutes. So the problem is already to process this data because we deal with big data. And not only to use the sensor to monitor and register these levels of concentration of pollution, but also to send this data from the sites to the server, then to process this data, then to get access to the processes data, and the highest level is just to warn people that this, for example, level of particulate matter pollution is too high, so stay home, not go outside your house. That's why it's very interesting to link. So first, sensors to special techniques to communicate between these sites and the server. Then the server to process this big data, and then to get access to this data. And not last but not least, to send the results to the stakeholders. For example, our stakeholders are in particular our city government. So we expect tomorrow to have some representatives from our city government because they are really interested in this system. Thank you.
I have some clarifying question. So I understood that the topography helps them later to recognize the particles, yes, on the real field. For that purpose, you need to the image provided here, right? Or
actually, when we speak about PM pollution, particulate matter pollution, we usually consider that this pollution is formed by fine particles of diameter 10 microns or 2.5 microns. Yeah. But when we try to look by using atomic force microscopy to the topology of these particles, actually, this is not a separate one. These looks like a clusters, and these clusters actually are formed by different types of particles of different nature. So it was surprisingly for us because we didn't expect that it's really like a conglomerate, clusters of together, right? Stick together. And the searcher will tell tomorrow that it's very difficult to use the AFM to get this result because it's okay, you can say.
Thanks. I'm going to just comment because we have not only the forces acting, but also the static forces coming. So that's why we have problem with choosing the right cantilever measurements. We get the cantilever stitch to the surface, and you have to choose wisely what's the cost cantilever will never need to match. So doing this is really tricky. So with time on this year, it's fun. And this one, so we go with this one. We have to choose differently. Maybe we can mass into some powers. We can, writing these comments.
Thank you, the answers.
So that's why. Thank you.
If there are no questions, I can, I mean, is the particulate matter pollution a big problem in Chisinau?
I think when there is no system to precise monitoring of this issue, so far nobody can tell you it's big issue or not big issue. When we will start the real-time monitoring, I think we can say, because okay, listen, I have a picture here.
In Riga, it was an issue.
Yeah, I think so, because you see, I didn't speak about this picture, but it's another story. When you know the La Palma volcano last year, November, we used our system to monitor in real time the level of pollution, and you can see here some very strange, but it's precise issue. Yeah, it's university here. Very strange peaks here. Yeah, and this is very high level in comparison with the average one. And it's actually about, I think, how long which slide is absent here? I think about 1 week measurements. So it's actually it's high level for about at least 2 hours. But nobody can tell you that this effect can have. Nobody. But 2 hours of very high level of PM pollution, I think it's could have a real impact on the health population. That's why after these measurements, actually at the end of last year, we had an idea to write this project, which will be presented tomorrow, and to ask for some support to create this platform to real-time monitoring, because this data actually tell us that you must know real-time situations.
We also have system for monitoring.
So far, I know only the site of the United States Embassy there is such system. You can have access to their data. The city does not have such kind of system. And in Moldova, I didn't know that somebody can tell us that you can use some other system. So up to my knowledge, it should be the first online real-time system for monitoring, environmental monitoring of the system.
The next steps would be how to deal with it.
How to deal with the pollution, how to expand the system at the scale of the Republic of Moldova, maybe north, east, south, and of course to integrate the system with the European Union system, because you have to exchange data. So far, I think we can take some data from, but these data are not generated here. So maybe some average data, and we work with some colleagues from Iași in Romania. Also, I know Iași is the closest city from Chisinau, is the biggest city one of the biggest city in Romania. They have such a system in Iași city, but this is not what we imagine to have here, because we imagine to have not only just to gather data, and but also to have a warning platform to communicate with people. Somebody's colleague.
Can we talk about Riga? The old city of Riga, it's the most clean one.
It's not possible to go there and start. It's called
But you said that it was a problem. It's a new part of Riga.
Around the city center, the old town is like the old town. It's a downtown, but around the city center, which is around the old town, it's very busy and there's a big traffic problem every day.
Yeah, so maybe.
You can see the traffic jams every day on the bridge across the river. And the same is happening also in the narrow streets between the tall buildings where the pollution is kept even more on the place because there is no air flow. Exactly. And it's interesting that we were involved also in some studies that you can see, and we assume that it is from PM particles. It's hard to prove, but if you go on the most on the streets that have the most dense traffic, on the buildings, approximately on the shoulder height, you can see like the scratch of color from buildings. And we assume it because of the traffic from the PM particles going back and forth from the traffic flow. There's like the scratches on the buildings. Yeah.
If you are scratching the buildings of the.
Yeah, I mean, because you saw it on the picture there, it's quite like.
Yeah, maybe.
Yeah, it's like microscopic dust.
Yeah.
Okay, thank you very much. Tomorrow we can continue our discussion. Having access to this infrastructure, maybe we can show precisely what we are doing. Thank you. About today, we have just a coffee break and then we go to the garden. And for our attendees, deci pentru dumneavoastră rugăm serviți cafeaua, deci avem pauză de cafea și mâine la orele 9 în blocul 4, deci va fi ziua finală, când în primul rând domnul Bătau va prezenta infrastructura centrului Carisma, inclusiv scopul de funcție atomică, defractometrul de rază X, Sergiu mai ai alte lucruri interesante și după asta vom merge în laboratorul de educație pentru drone și acolo vom prezenta și proiectul de transfer tehnologic, inclusiv unele momente practice, cum se primesc graficele respective care vă le-am prezentat în sensul fotogrametriei terenului. Deci cu dronele se iau imagini, este soft special și cu ajutorul acestui soft se fac aceste imagini tridimensionale foarte frumoase. Deci, iată, asta va include ziua de mâine, inclusiv pentru participanții fideli, domnul profesor Dapunte a semnat certificatul de participare, deja e semnat, deci mâine trebuie să fim toți prezenți ca să vă le mânăm și să facem fotografii frumoase pentru evenimentul nostru. Deci asta este, da, asta este cam programul care noi trebuie să-l facem pe parcursul zilei de mâine. Deci, stimați colegi, vă rog, vă invit la cafea, da, vă rog. Blocul 4, deci este strada Mateevici. Da. Deci, noastră, în blocul 4, da, blocul 4, deci chiar în hol, noi vă întâmpinăm, fiindcă centrul de cercetare este la etajul 1. Noi vă întâmpinăm în hol. Da, partea stângă în hol. Cum intrați pe stângă. Și mai departe, deci veți merge cu noi, deci nu vă lăsăm nici mâine. Fără îndumarea noastră. Mulțumim foarte mult. Da, vă rog la cafea.